So hello everybody, hope you can hear me well. And so let's start by downloading the 11.2 template from the Jamboard. I also posted a link here for the template and the dataset. So the template itself, the link is this one, and the first one was for the dataset. And depending on your PyTorch version, there was a problem with the this kind of dataset extended MNIST. So it would be great if you could download that template from 11.2 or get from the link in the chat and try to run it. Because if you try to run it, it will try to it will not work, of course, but in general, it will try to download first this dataset from the links that they have inside this code. If we go in here, we see there is a link. And in some PyTorch versions, this did not work. So the one thing that is possible is that I think you could even like edit the source code of this part to change the link. This link basically works, so I can give you the link that works, because if in your version it doesn't work, you can try to change it or download it directly. So if you download it directly, then the structure would look like this, where you have the extended NIST, the data MNIST, then the processed with all of these things, and then the row that is empty. So it automatically downloads the row and then sets it to the processed. So yeah, let's start by this one. So please let me know in the chat, did you manage to download MNIST by running script 11.2 plus minus. If there are some problems, let me know, and then we'll move on to actually the workshop itself. And if there is problems, you can try to update the PyTorch. You can try to use the link. Let me know how you succeed. Wait in the chat. So if it's still downloading, that's fine. Even if it's downloading and not interrupting, that's great. So we can work with that. I mean, we have to cover the theoretical part, and then we'll start coding. So that's great. About like people who are posting minus, maybe you can explain a little bit what exactly is not working, and maybe I can help somehow. So we'll wait maybe for some more responses. Okay, so for the people who are saying that it's downloading, hopefully working for those of you engaging. So before we start, one thing I posted in the Google Classroom, the situation with the marks. That's great. I saw that a lot of people resubmitted the works and got up to the grades. So now it seems like that at least 5 people are able to pass the course, and some of them, like at least 3 people, are above 70% now competing for the best student. Sad to see that the best one, the girl who was the best one all the time, went down a little bit in the scores. Hopefully she will get back. Then we have also Gins, of course, then Kristaps, one of the Kristaps. Yeah, so you can check out the markings in the Google Classroom yourself. If there are some disputes, you can write to me in email or in the Google Classroom, so let me know. But in generally, like to pass the course, we still have ahead of us like this week, then the next week, and then the week after, and then we're done. So there is not too many sessions ahead. At the same time, they will be very intense. So please do not put this to the last moment when we'll have to do the marking for the final mark of the course. And also the great thing is that you can keep working with all of this, and actually, so those interested can join a lot of research projects that I'm currently involved. So anyway, let's keep to this topic. So the topic is the autoencoders for today. So these are the first of the unsupervised models that we are looking now. So this illustration is from LeCun. So the LeCun is one of the like seminal, very important figures in the deep learning. So he, in the 90s and even before in late 80s, developed a couple of fundamental models that are now used everywhere. And he's right now I think in the Facebook research. So anyway, he has this kind of illustration where this is like a cake. The deep learning is cake, and the unsupervised learning, the way how the kids work, the children learn, is the way that we don't give labels for everything around the world. I mean, like, for example, when we made the classification or regression models, those are the supervised learning, because we give the labels or the ground truth, and we say this input means this. But unsupervised learning is as kids learn, they can associate all sorts of things themselves, and they don't need label for everything in the world. They can kind of understand that if this object is similar to the previous object, then probably it has the similar properties, it can do the similar things, they can explore without the necessary of the labeling or enforcement. So and this, as in the LeCun's idea, the unsupervised learning is the most important part, because we cannot label all of the data in the world, like everything, like every single bit. We need some kind of way to do this without giving the labels, to learn the logic without the labels, just using some additional information from supervised learning and from the reinforcement learning. Reinforcement learning will be 2 weeks ahead. This will be the last topic we cover. We will cover the whole cake, basically. Here are, of course, a lot of parts missing, but at least these are kind of the fundamental ones. The reinforcement learning is a specific type of deep learning, or even without deep learning, machine learning type of models that do not require the labels again, but it requires the kind of reward value signal. So it's a idea that you have computer game where you get the score when you do something right, and you get the minus score when you do something wrong. And the model can learn all of the decision making, everything, how to interpret the world, what to do step by step, just using this one very small signal that is even very sparse sometimes. Like maybe you can get the reward only when you complete very difficult tasks that requires like hundreds of steps or thousands of steps. So that's really powerful, but at the same time, the reinforcement learning itself kind of do not cover all of the other parts of the world. Like the reinforcement learning itself is probably not sufficient enough to cover, to interpret and encode everything we see, everything that is in the universe and stuff. So that's why there is this bottom layer, the unsupervised. So by the way, if you have some questions, ask in the chat. We will move to the next step. So I guess first let's look at what the autoencoder is and how we can use it. There will be multiple use cases. The autoencoders and these kind of models you can use for so, so many things. That's because they are this bottom part of the cake. You can use them either for the supervised learning, for reinforcement learning, for zero-shot learning, for like generative models. There are like many ways. So here, this is what we have as a very simple autoencoder. The first part of the encoder we already know. So if we look only at this part up till Z, this is a like very basic classifier model that we already did. Like when we feed in the image of the letter, or let's say in our case there was the fashion MNIST, the trousers or dresses or whatever, we classify what it is. But in this case, we don't classify it at all. We don't have any labels. Like it can be anything. This can be, the input can be like cartoon character, it can be just random pictures or whatever, and the output is the same picture. So our target data that we will train our model is the same picture that comes in. So the model should compress all of the information to very short vector Z that is low dimensional, and should then deconstruct the model and create this reconstruction. So this decoder part is something new. With the coder part, we can do the coder in many ways. So like one of the old ways how to do the coder would be, so let us add some information about the decoder. And by the way, if you have questions, let me ask. We will code this just in a second. So decoder, the one that was the old style is using the transposed convolutions, transposed convs, conv2D, or the deconvs. Some frameworks call them deconvs, but they basically, as you remember, when you implemented the convolutions, then you remember that we have the dot product, and if you transpose that dot product, you can easily basically get the kind of like based on the channels, the outputs of so yeah, the width and height. So here there is another small image maybe of how it works. So you have input that is smaller, you have kernel that is learnable, and then you would kind of, in this case, without dot product, but basically there is a dot product, you would apply that same input value for every cell in that kernel, and then would calculate it out in the new feature map, and then you would go with the stride and do basically the same thing as before for the reduction. And there's also a formula for calculating the output width and height, but in general, like that is just for you to know that something like that exists. But like for some time already, I think NVIDIA started doing that, but then others as well. The kind of new style is using the some kind of up sampling, like bilinear up sampling, bilinear up sampling. Again, this is something that you do not learn at all. This is just a very like just an algorithm basically I also should fix the so bilinear without 2L. So that is simple image algorithm that you can use to upscale or downscale any resolution images. There are like actually multiple ways how you can do this. I think there's one of so the other way is nearest neighbor method. When you have options what to choose as your values for upscaling or downsampling, you can choose different kinds of methods, the algorithms. Maybe I can find some example just in a second. There should be some good image, hopefully. I guess there's one like this. Just a second. So it's uploading very slowly. So there are few methods that could be used. So you have low resolution image and you want to make it a little bit higher resolution, then you could choose that value, pad it with zeros, then kind of shift the values, for example, or just use the nearest neighbor. So these are just, you can imagine as some kind of filtering techniques for upsampling the same image. You can just repeat that value one, for example, in the same sector, and then calculate average. So that is either it's like a bilinear upscaling or it's like just like average upscaling. Any kind of upscaling basically works better than the transposed convolutions because they're also prone to do the checkerboards. That is, if you type in the Google the transposed convolutions or convolutions checkerboards, you will see that there are some artifacts very common with those, and yeah, they are not good anymore. So they were good when they started building these models. Then the new style is first to do the upsampling. So it's usually like 2 times, for example. Then the second part is using the convolution 2D that do not change width and height, and also do not change probably channels, but I think the channels they change. So usually then the channels get reduced. So reduced, for example, 2 times, or basically by some factor. So let's say reduced by n. So for this style of decoder, my question is what kind of convolution 2D parameters should we use to not change the width and height? So what kind of params should we use for conv2D to not change width and height? So that would stay the same width and height feature map. So the params that I want to see is, so there is a padding, right? Then there is a stride. Then there is a kernel size. There are a few others, but let's use these 3. So please type in the chat. So what should be P, what should be S, and what should be K in order for the input width and height not to change. So for those of you who did the homeworks of the convolutions, this should be super easy question because we did those kind of convolutions already. So do we have any ideas? But wait, if no ideas, type in minus. So the answer for this one is using this formula that you see here. This is inverse formula, but we should then, maybe it would even work with this one, I'm not sure, but we should use the formula in the forward direction. And if you plug in the formula the kernel size, so there might be even multiple answers, but in general the common answer is kernel size 3, stride 1, and padding 1. If you add those as your parameters and plug those inside the formula that I gave you a few sessions ago, you would see that width and height do not change. Like, you can pass the convolution over that one. So there is another fun thing. So somebody is writing that stride could be 0. Stride actually could not be 0, unfortunately. Otherwise there would be no point of convolution, because you need somehow to move over so the stride, you cannot have the stride below 1. You need to have some kind of step size when you want to move around your feature map by your kernel. So if you don't understand this, you definitely need to do carefully your homeworks with regards to convolutions and go back to that section, that lesson. So the idea is that we implemented the for loops even, where you have the kernel like going over the image, like with the small step size stride, and we apply that kernel using the dot product basically over all of the image and produce a lower resolution image usually. But in this case, and this image is called feature map, but in this case we don't want to change the width and height, and that's why we choose these parameters: kernel, stride, and padding. I think it might be that there are some other parameter combination that could give the same result, but in general this one is super common. So if you see this kind of combination, that is very common combination. Anyway, so let's move on to the next step. Not very happy that you didn't know that, but still, so that indicates one thing that you need to learn with regards. Go back to the convolution session, because we calculated. I know that some of you right now online, you calculated yourself the width and height outputs. And if you calculate them, then you should kind of understand that you can choose the parameters to have that width and height do not change. So some of the properties with regards to the use cases, why we need these autoencoders and how you can use them practically. So one is the anomaly detection and re-identification or classification, basically. So let me add some examples and explain. So when you train your data set, your model on a data set, you can later apply it on some other data set that was not used in your training data set and have those z vectors. So here the z vector is in 2 dimensions, for example. Because now we can plot it very nicely here. And by the way, in our today's task and also on your homework, you could have the Z shape in some like 2-dimensional space as well, but that would be really hard to learn. So here there is a batch, comma 2. So that's why we can plot it nicely in the plot here. And you can see that Now let's say that these are the batch samples, and there are some that are normal and some that are not normal. So the inputs can be images, but the inputs, of course, can also be some kind of time series. So next week we will look at time series and time series prediction. Like for example, when you want to predict the stock markets or something. And then the decoder part is also cool. That when you can detect which cluster is good and which cluster is not good, you can deconstruct it. I mean decode it. And then see what is what the input would look like when it's not normal. You can even simulate that maybe at some extent. And yeah, so in the way how you would calculate the difference between the green ones and the yellow ones would be probably for the simple autoencoders. I would advise to use the cosine distance. I will give formula a little bit later. That's basically a dot product as well. So the cosine distance, and you can think of it actually as an angle. So if you have like huge dimensional vector, like let's say 512 dimension vector, and if you want to see what is the difference between this point and the green one and the yellow one, and there are 512 dimensions, not 2 dimensions, then one of the best ways how to compare them would be to calculate the angle between them, and that would be then the cosine distance. And that's how you can like calculate the kind of clusters of them. That's one way. And maybe I add another image for this use case. Actually, this one actually have the distances as the angles, and those would be cosine distances probably. You could of course add the arc tangents and calculate actual angle, but that's not necessary because cosine distance from 0 to 2 also quite okay. So here there is an example. You have the training phase where you have the autoencoder, of course, and then you have the test phase where you have unseen normal pictures and unseen not normal pictures. And then you can see that the difference between those z vectors can be measured in the angle, right? In either a degrees or some distance metric, and you can compare them automatically without need of any labels, because later then you can have like doctor to say the doctor that please list me some images that are like bad ones and that are good ones, and you can feed the model, and you don't need all of this kind of labeling process at all. So again, this one is an example of the ray identification, the anomaly detection. Of course, you can use this, for example, for biometrics, that you would have some samples of faces, for example, and then see if like Apple Face ID or something. So is it clear so far? Is it clear so far? So plus, minus, if minus, please let me know what is not clear, and then we'll go to the next part of use case, and then we'll start coding. Okay, great. I see 2 pluses coming in. That's great. So hopefully others also can get along. So the other way how you can use these models is using, for example, a generative case. So this would not be actually really great generative model. the simple autoencoders are not powerful enough, but theoretically you could use it as a generative model. Like, for example, you have heard about the GANs, right? The generative adversarial networks. So this is actually very similar to that. So the GANs also have this kind of decoder there from the latent vector Z, actually. So you already like half understand the GANs already. So what is latent in comparison to mean square error? Just a second. So generative use cases. That's one. Also, you can use that for the pre-training. For the pre-training, it's more like in the previous slide where you would delete the decoder and just use the for the pre-training, that's the encoder part, and for the generative use cases, that's a decoder part. After the training, of course, both cases after the training. So the pre-training is great for reducing the time you need to calculate to train the model. Basically, for example, normally you would train model with 100 epochs. Now you can train it with 10 epochs because you just pre-train it on unlabeled data in the same domain. Actually, and the last thing is basically also the extension of the data set. It's sometimes called semi-supervised learning. Extension of the data set, semi-supervised learning. And in that case, you would probably use, again, also the encoder just. So you would have the images that are somehow similar to the labeled ones, but they are not labeled. And then you can use them for the training, the classifier, for example. And this method would be much better than the just using the classifier itself to extend the dataset, because if you use the classifier itself to extend the dataset, you have the bias of the training dataset. But now, if you train on the all data where you have the labeled and unlabeled, you get a really cool situation where you can kind of learn the generic features. So that's why it's great. So you can extend your dataset, but even if you have 100 samples, now you can have thousands of samples just using unsupervised learning. So what is latent in comparison to mean square error? So maybe you think about this L2 here. So the L2, sometimes you add L2 to have the unit vectors. So if you have the vector that is length of 1, so then that you can achieve by normalizing with L2. That is not mean square error here. Then here the mean square error is calculated from the x and x prim or y prim, so the input and output, and the L latent, that seems like in this image is some kind of a memory bank here. There is something there. So again, this is something that you can research. Basically, all sorts of developers around the world are thinking all sorts of models. You can of course add the losses from any part of the model. You can train the loss from this part, from this part, from this part, whatever. They will all be summed together. The gradients, the error gradients will be summed together, and then you would execute the stochastic gradient descent. We already calculated that by hand, so you should be understand that the loss is not always tied only to the output. You can have it even also in the middle part. Hope that answers the question. If not, then like clarify a little bit more, and I can happy to explain more. So the last thing missing here is the new dataset. The new dataset is the extended MNIST. Again, the LeCun was the one who started working with the simple MNIST with 10 numbers, right? So, but this one MNIST is much larger. So you have in the one of the versions that we're gonna use, you have 800K samples. So that alone is quite cool, right? A lot of samples. Then there are 62 classes of these letters and numbers, and there are subclasses. So you can go back down to MNIST, where there is just the numbers. So if you have just the numbers, then there are 10 classes. So the original MNIST that is already here for, I don't know, like 30 years or so, so really long time, that one have only 10 classes, the digits. And the letters, like if you just look at the letters itself, I think that was 26 classes. Letters by type, there is 26 classes, I think. So there are multiple ways how they split this data set. We'll use just one of those ways. So for example, here's another way how you can split it. You can just use the similar letters, like as a lowercase c and the uppercase C. That is very similar. We don't split it. The I also, or there are some ways how to do this. So we'll use this data set. That's great. And now let's move to the code and try to implement. By the way, I will add in the Jamboard what we're gonna implement. So we're gonna implement the encoder part as well. So there will be an encoder part of the model. The encoder looks like this. Hopefully I don't have a mistake here. If I have, then I will fix it later. So I tried to put it so that we don't have a too long sausage. So here, the encoder, nothing surprising here. There is a group norm that we talked already. That's really powerful way to normalize everything. Then we have at the end, the tan H that is optional. It's just limiting factor so that the Z vector would not go to the infinity. There would be some kind of reasonable, kind of, let's say, the limits of the Z vector. But there could be also L2 norm, as you saw in that previous picture. There can be all sorts of limiting factors. So that's one. Then the decoder that we're gonna code. So I hope that I made it in a correct way. I see the group norms. Yeah, I see the upsampling. Okay, I was looking at the upsampling, I could not see it. I was a little getting scared. So I made the scheme for the decoder, and the upsampling is here in the bottom part. So there is a bilinear upsampling. So that is just like the so you have small image, you may make it bigger. Add like all of the missing pixels as zeros, and then calculate the average between those pixels or something. That would be kind of very simple bilinear upscaling. There would be also other methods how you can do this. So that one. At the end we have sigmoid. So the sigmoid, so let's ask a question here. So what does it mean that we add the sigmoid for autoencoder at the end? Like what does it mean, like for our situation? What we should take in account if we add the sigmoid at the end for the autoencoder? If no IDs, then type minus. If no IDs, why we should use it, then minus. Okay, so the sigmoid function, so the way how to answer to this question is to think about the function, sigmoid function. That is something that we already looked multiple times. So regarding the input, for every pixel we will use the sigmoid function, and the sigmoid function output, if we'll add it here, is always from 0 to 1. So that means that the x must be normalized from 0 to 1. It can also be normalized from -1 to 1, but then we need some other function that you already know. So here there is the so must be x must be normalized from 0 to 1. Otherwise the loss and everything will not work, of course. So that's one thing. Then the loss function, for this time we can use the mean square error. We can use also the mean absolute error. We can use even the depending on the way how the data is processed, maybe sometimes we can use in the 0 to 1 range the cross entropy, or binary cross entropy actually. But so Ginz is saying about the probability, yeah, sometimes when you see the sigmoid you would start thinking about the probabilities, especially in the range of binary cross entropy. But there is also one but. These, if you look at these images here, they are actually not sharp. So the binary cross entropy and cross entropy works properly only if you have zeros and ones. But here you have something in the between, like probability of, let's say that would be 0.5. For that kind of probability you should use different kind of loss functions. So they would not convert, like they would not converge to 0 using the binary cross entropy. So either you could maybe also like, for example, discretize your input images and then you can use the binary cross entropy. So, and sometimes for the decoders in the papers, they actually prefer that kind of loss function. You could probably somehow, actually the KL divergence would be much better, but we will talk about that later. So anyway, so this is what we have and what we need to do, and we also will implement the saving of the weights. So when we have a good model of the test case, or the test data set, we should save our model. And as a homework, I will hopefully make the pre-trained model that you can use to do the classification and the ray identification using the cosine distances of the z vectors. So I will prepare a template for that. Here we have a dataset. The dataset returns just an x. So later we're gonna make a little bit change in this model that it would not return only x but also something else. But here, in this case, we don't return any labels. So x can be anything, like x can be any letter in the alphabet. So that's quite cool. So that's one thing. Then there is a train test split. Then we need to implement the autoencoder. So let's try to implement our autoencoder. By the way, it returns the out and z vector, of course. The z vector is also interesting, right? So here I have some dummy code to test the autoencoder. So if I add the breakpoint here, hopefully it will not crash. So let's see. So let's implement the, according to the scheme, the autoencoder. So there will be torch and n conv 2d. I will write everything in one line so that we have a bit better visibility, but I would not recommend to write everything in one line, then let's be spaghetti type of thing. So here the in channels is the same as in fashion MNIST. We have just grayscale inputs, so this is one channel. The out channels, as in that scheme, would be 4. The kernel size could be 3. Stride would be 1, and padding 1, and that means that this one is not changing the size at all. So this is the same size as an input width and height the same size as output width and height. Only the dot product helps us to produce more channels as we implement it ourselves. So then the torch and leaky ReLU, and with the negative slope of E minus 2, then the torch and groups. So the groups, there is one caveat. The group number should divide the channels, if we remember how it works with the groups. So they are grouping the channels together. So there will be automatically learned 2 groups for those 4 channels. They are not batch size dependent. So the batch norm is much worse. So batch norm would require large batch sizes. So this one works great with any batch size. Like probably very small batch sizes would not be great, but even like in some of the models that I forgot to mention that these kind of models are used also in Tesla, as far as I understand. So probably not the simple autoencoder, definitely not, but they say that, I remember in the conference that they train with batch size 1, so the batch size 1 would work with the group norm. Then the other thing is that they use these kind of encoder models for generating Z vectors, and basically what you can have to do is like let's say the Tesla comes across the camel on the streets. I actually think that was in their press conference some few years ago, or maybe 2 years or something, or 1 year. I'm not sure how long. This was not too long ago, where like the Tesla sees the camel for first time, and then people in the headquarters say that we need more images of camels. So they produce a Z vector for this image, and asks the whole fleet to send the images that produce the Z vector with the sum distance of cosine distance of the Z vector, and they automatically get like thousands of camel images, and the same for all other types of situations. So these models are quite powerful to extend your datasets. So you can look up the press conference with Karpathy, I think. So Karpathy is actually right now the main guy for Tesla AI, and he's done a lot of cool research so far. So okay, this one is like that. We just changed that one line for the in channels. Then the next one is the reducing of the size. So we can reduce size again in multiple ways. Let's see what we have here, but I don't want to use something that would not be in that scheme. Let's use that was in the scheme, the average pool. So the average pooling can be done the same as we did with the adaptive average pooling, exactly the same thing. We can calculate ourselves the kernel size and the stride and the padding, and the adaptive average pooling does it automatically, but we can have the predefined version as well. So here we're going to use the predefined version, where the kernel size, stride, and padding 0. If you add all of that in the formula that I gave you a few sessions ago, you will get that the output is 2 times smaller than the input. So that's great. This part is okay. So I think then we just need to copy a few times all of this stuff, or maybe the smarter thing would be probably to use sub-module. Maybe I should show you how to use sub-modules here, because the sub-modules would make your life a little bit easier. So let me see, 1, 4, 4, 4, 8, 8. So there will be 4 groups. Okay, let's make a sub-module. So the sub-modules, I'm not sure, like I think in some part I gave you, asked you to do this, but we can do this here as well. So there will be the sub and let's say encoder block, block. So we don't need to copy the code many times. That is not efficient at all. So we can just have this small sub-module. The sub-module can have its own encoder, of course. So this can be everything that we have here. The only thing is that we should have the, so there should be a, let's see. So in some cases there will be num groups a little bit higher. So let's see, there will be num groups, there will be in channels, of course, there will be out channels. What else? Out channels, maybe we should add also, because at the last stage we don't have an average pool there. Maybe we should add this actually, then the module list. Let's see, okay, I cannot do it like that, but maybe I can. Module list. Let's see, the module list wants the modules as the iterator, so we can add it like that. So this will be a module list. And the last adaptive pool we can add later, like that. Of course, it's not required. If you want, you can copy the code n times and make it as you wish. So here we can add also is downsample. So and then if is downsample, then we add to the encoder the this one. Otherwise not. So here the in channels are going here, so we actually can just delete that part. And the out channels go here, then the out channels go here and here. Okay, I need to set it like that. The num channels also here, and the num groups here and here. Hopefully that will be enough. Maybe I have some mistake, but I hope not. So this is like 1 to 4, then 4 to 8, 8 to 16, 16 to 32 channels. So, and then we need, of course, the forward pass, def forward. I will add this in Jamboard in just a second. Forward, so you can carefully try to write this code, or even better, use the code that I gave you just in the schema. So like that. Okay, forward pass here, and the forward pass, of course, is just the forward to the encoder. I think I already saw that somebody is trying to. Okay, so I see some question in line 74. The in channels should be equal to. So no, the line 74 would not work with in channels. Anyway, but nice to hear that you're looking after the code. That is really nice. I think in some previous sessions, some of you helped me out of fixing on the live session some code, but I hope this one is okay. So I will add this to the Jamboard, slide number 9. So this will be our small encoder that we can module, that block that we can repeat. This is the same way as it works in the ResNets and other types of interesting models where we have blocks that we repeat. They have some interesting properties. We don't have time in this course to go in depth of all of those properties, but there are really nice properties to that. So we can then use this as directly as the module. So the encoder block. The encoder block, by the way, is now on the Jamboard, slide 9, if I remember. Yeah. So the in channels here is 1. The out channels is 4, the num groups is 2, and is downsample is true. By the way, the last parameter, again, like I have seen many times, the people write code where they just don't show the what kind of value they give us, true or false, the parameter name, and then the code becomes totally not readable. The same probably goes for the other parameters, but I think for the booleans especially, very hard then to understand what you mean by that. So then there's encoder. Here it goes 4, then 8, then 2, downsample true, then 8 to 16 by 4, I remember correctly. Yes, 4 groups. So with downsample true, and then the last one downsample false, and this will be from 16 to 32 by those 4 groups, and then we need 10h at the end, torch, and n 10h at the end. The 10h function goes from -1 to 1, of course. So this one would be the encoder part. Maybe I will drop in encoder part as well in the Jamboard. Okay, then the decoder part. Again, I suggest that we should make a decoder block. The decoder block would be easier to manage. It's actually very similar to encoder block. So this will be the decoder block. And of course, you can imagine that you can have this so many layers, just make it like with some kind of for loop and some formula that you calculated. So there's going to be the in channels, out channels, and the up sample. And this will be changed to upsampling bilinear. Here you can have also the nearest neighbor. And here we have the scale factor. You can have it too. I think you can also fix to some specific size. So the module list forward, what do you mean? So you need to loop the module list in the forward pass. No, I don't need to loop it. I hope I don't need to loop it. The module list, if I add here on the forward and go inside here, I hope maybe you're right. Let's see. So no, this is not the module list, sorry. So the module list, I would expect that it's implemented. We'll check it just in a second. Okay, it's not implemented. That's fun. Seriously, it's not implemented. Nice comment. Thank you, Henry. You're a smart guy. Thank you for helping out. Seems like it's really not implemented. Cannot believe it. I think it thought it was. Probably I could convert it back to the sequential. Let me think. Maybe I don't want to do the for loop. That's why maybe I can somehow quickly convert to the sequential. Maybe you can give me some code. Torch module list to sequential. There should, I think there was some kind of syntax that you could do this very quickly. Ah, nice. I can do this with just one line. That is great. So let's do this. Thank you for letting me know that you need that one. So the line for this one would be here something like torch NN sequential and passing the encoder. I think it would work like that as well. At least I see some code. Let me double check. I'm just a little bit not too confident about this conversion, but let's see. Okay, basically I don't like it, so let's remake it. I was not I kind of either I was not aware or if I forgot that you don't have the forward pass implemented. So of course one is that you can have the for loop, but the better one would be just have the list here. Then there would be encoder of this one, and then we just use here the parameter sign, so that this will just make that all of the list elements are just the parameters for this constructor, and now it will work great. So that is really interesting point that I was missing, and I will add this to the Jamboard, the fixed version here. Thank you very much for pointing this out. Again, really good if you use the some kind of like development environment like PyCharm, where you can see when you can just click inside the function and see how it's implemented, and if there is a forward pass actually implemented, or they want you to implement the forward pass. In this case, I did not want to implement the forward pass, so this will be fine. Also, the decoder block, we also need to change it a little bit. So this will be the decoder. This will be just a simple Python list with the upsample, where we would also append here the decoder. And then we will have the decode self decoder. That is the torch sequential that we will pass list as parameters using that decorator here. And then we will also pass here the decoder part. So that's great. Thank you for letting me know. So here there is the in channels, leaky relu group norms as always, and here that one. I hope that part is okay. The only problem is here that there will be need to change around a little bit in and out channels. So there will be the first one will be the out channels, the in channels will be out channels. I don't like it. So let's flip it around. So there will be in channels will be in channels. There will be in channels I mean there's out channels. Then here the number of channels for the group norm are in channels in this case. So there will be 32. So Z vector will be 32 dimensional. That one. Then there is in, out, and out. Hope, great. So that's great. I think that's about it. So I will add the decoder block as well to the Jamboard. So we have this simpler model, and tomorrow we will work with the much more advanced model. That one will be the variational autoencoder that will be with the proper generative features. So, okay, Henry is helping me with another thing. I just use sequential instantly. Okay, yeah, you can do these inline scripts, and the inline scripts sometimes are good, but sometimes they make spaghetti. So I'm a little bit not a big fan of inline scripts in general. The inline script, what Henry is saying is that you could write something like if like just in one line, so there would be some layer, so it could be something layer if something is upsample, else some other layer, or maybe none, or anything like. So then we can just write all of the if statement just in one line in Python, but that is not really readable in many cases. In some very simple cases it's okay, but in general better to make readable code than try to optimize your code before before the interpreter itself. So the decoder block, the in channels are 32, of course. The out channels are, in this case, 16, right? The number of groups are 4. The is upsample true, right? So then we copy this block a couple of times. This can be also automatized if you want. So then there is a 16 to 8, 8 to 4, and this will be then 2, I guess. So let me check if I'm following up everything. So there I have the 4, then I have 8 to 4, then I have 4 to 4 2 times, I think. 4 to 4 2 times. So there is a little variation. I hope that my code matches what I have in the schema. If it doesn't match, sorry, maybe there's some small variation. So there will be 4 to 4 just one more time. Then there will be the torch NN adaptive average pooling to because the upsampling is not really precisely the size that we want actually at the end. I think it is like, so it's the beginning, it's 1, then it's 2, then it's, so this will be then 2, then it's 4, then it's 8, then it's 16, then it's 32. So let me double check if maybe it's not what I was expecting. So the first one will be so 1 to 2, then the next one will be 2 to 4, 4 to 8, then 8 to 16, and the next I need actually another one. So this will be then to the size 16 to 32, but we need 28. We will not work with 32. So one is that I could calculate the kernel size, stride, whatever, or I can use the nice function that does it automatically for myself. So the 28 and by 28 is the target size. That's great. Then the last thing is to add another pass of decoder block. So I guess it will not be exactly like in schema, but we can add it here. So this pass should then reduce it to the channel size of 1, and the upsample should be false, and I also must check that if this would actually work. So the num groups, then here I guess I should add some kind of limiting factor. So let's add some limiting factor here. So either this will be minimal of 2 numbers, the either num groups of our channels. By the way, again, if you submit the code just using my schema with a lot of copied code, like a lot of lines copied, I will accept that code as well. But I just don't like to make it so many copies. So I will add this one to the Jamboard slide number 10. I will also probably drop the Jamboard link in the chat here, because probably Henry don't have the access and some other people may be watching. So the Jamboard is here, or maybe in the description. I already had it probably, so I forgot about it. So the slide 10, I added that part. Jamboard, okay, okay, great. So that part is in the slide. Okay, great. Decoder, and the decoder here, there is one part missing, the sigmoid at the end. Torch NN sigmoid. I don't like that my padding is a little bit screwed, so let's see. So if I, okay, tabs, now it works. So the Python tabs, very important. Okay, so hopefully this part of the code will be okay. I have actually dummy code just below to check if my code is okay. we'll see. If it's okay, then I will add it to the Jamboard. So then the calculation of Z, self-encoder forward X, again, please do not ever write like this encoder with the operator overridden of the bracket, because if you write it like this, this looks like a class function. This is not a class function. This is an instance of the sequential, and then I want to call the class function forward. Basically, we want a code that is readable. I have seen that students sometimes do this because in the you can do this, of course. There is override in this operator, but it kind of makes it not readable as well. So then we should like flatten the Z vector to those 32 dimensions. So to flatten Z vector, again, last time we already talked about it. You can have the -1 by 32. You can. This is exactly the same flatten operation of looking at this as the batch size by 32. This is exactly the same as the batch size by -1. So hopefully you get the syntax. It automatically calculates the kind of appropriate shape just with that minus of multiplying all of the rest of the shape values. So here the Z out of before this operation shape should be actually the batch comma 1 batch comma 32 comma 1 comma 1. So that should be the case, hopefully. I need to double check it. I really hope that that's the case. We will need to run the code and see. So, but then we can of course reshape it like that. Then for the input of the decoder, so here the decoder Z, we again need to reshape it. So if the Z was like that, then of course you can just make a copy of it before, but just to make it clear, we can reshape it like that. And then the out, or in this case it's like Y prim in this case, but it's sometimes called X prim, X hat, Y hat, whatever the prediction. So self-decoder of forward of Z deck, like that, and hopefully it should work. So I have a breakpoint here, I will run it. If it will not crash, everything will be fine. I will copy the code to the Jamboard so you can catch up. Okay, it works, and we need to double check what we get out of it. Okay, there is a bug here. The Y should be actually Y prim comma Z. Of course, I can unpack it later, but it'd be nicer to see it immediately. And here, this is the first model that you can start using the tensor board that I showed you last time, where you can have the projector to like plot in the tensor board this really cool stuff of embeddings, where you can see the embeddings with images in that plot. You can use the Z vector for that. That's great. So the Z vector seems to be okay, hopefully. So 32 batch size by 32, I guess. Let's see, what's our batch size? So this is not okay. That's why we should run the code and check. It should not be 32. So we have the fun thing is that everything works actually, but this is not the right shape. That's why you should track the shape. So here the output again is not okay because we are missing the batch size. Oh no, we are not missing the batch size. Sorry, my mistake, my bad. Here everything is like, I guess, okay, because here if I add the batch size as it was in our original batch size, not in dummy code, then everything should be fine. But in general, these minus signs are super dangerous. If you use them and there is something not correct with your model, everything could work, but you could start mixing and matching your batches together, batch samples together. If you do that, then this like path to the serious problems. So here there's the Z shape is 128 by 32. That is what we expect. The output is 128 by 1 by 28 by 28. That is what we expect. Everything is great. So I will copy this part of the code. So let me add all of this in one screen. I will drop this in the Jamboard so you can catch up. And now we are missing only the loss function to have really dummy vanilla autoencoder ready. So this guy is not very smart. So this is one of the dumbest autoencoders we have. But we will make it a little bit smarter by the end of today. And then tomorrow we're going to make a lot smarter model. So this one is in the Jamboard then. Then the loss function. Okay, funny stuff. I should update my templates. I will definitely update my template now. I don't like it at all. So my template, sorry, I dropped the Jamboard stuff as well. So the first one thing, I don't know why did I add here the loss function as the torch NN. That should not be there. Then the batch size also here, the batch size. So anyways, I will update template later. So here, the loss function should not be here because we wanted to implement it by hand. In that way, we understand better the loss functions because you can make all sorts of cool loss functions yourself, much better than the default ones. So here, there we could use the torch mean. So this will be just a simple one, x minus y prim. So we are training on the same input. So the input should match the output. So then we would add the squared, and this should be it, hopefully. Except we need also to save the model at the best loss value. So usually you want to save your model when you reach the best performance during the training, because as you know, a lot of bad things can happen. One of them is the overfitting, another is the catastrophic forgetting. So in the deep learning, there is such a phenomena when you train your model and then like at some epoch the kind of like gradients cross some kind of threshold and you forget almost everything that you learned and the loss starts rising very rapidly. In some cases, the rising loss is actually a good thing. So the adversarial kind of models, one is this variational autoencoder that we'll look tomorrow. There is one part of the loss that like decreases and then increases naturally. So we want our loss to be 0, but in some cases it's acceptable that it rises. It is by design if there is adversarial component. Also, sometimes it's acceptable that the loss do not go to the 0 at all. So anyways, here the way how we save at the best loss. So we'll have here something interesting. So let's make it very dumb simple. So here there will be the best loss. That will be the float value of infinity. So that is really bad loss in the beginning. Plus infinity. So then here, when we are in the test stage, we can use the same code as above here. When we are at the test stage, we want to look at our loss. So if the loss that should be then moved to the CPU, we already have that code actually. So let's use just here some kind of small loss scalar from this one as -1, the last element from that one. Basically, you can write it as you wish. You can have the loss CPU item or whatever. So the loss scalar, if this loss scalar is smaller than the best loss, then we can write the best loss should be loss scalar, and we also want to save our model. So the saving the model, you can use the something like torch save, and there is also a torch load to load the model. First you create an instance, and then you save your, then you load your weight. So to load the weights, you can use the model save dict like that, and then also the we should have the path. Maybe I should put it step by step. There is another important thing here. We'll look at it second. So there is the, let me go to save. Sorry, I will go back just a second. So there is a path and some other parameters. So this will be path, I guess. No, what's the name of that? F. Okay, I don't like F. So this will be just the best model PT, so the pickle value. If you know about the Python, you can serialize the binary value, like objects in the pickles. So that is one way how to do this. So the one thing that I don't like is we should move somehow. I think it was in the state dictionary to the CPU, or maybe you can just, okay, the best way would be actually to use it like that. So just, so the model, but actually this is dangerous. Let me check. The CPU applies parameters to the buffers of CPU, so that is the container. That might not work as expected, because maybe it will just change the CPU for the pointer itself. We need to check that. Maybe if by any chance the model gets moved to the CPU after this line, then you should move it back to the GPU. So model then would be model to device. So if in that case, but hopefully this line works fine. Hopefully it makes a copy on CPU, not just use the pointer. So the pointer to the instance of itself. So anyway, if it doesn't work, you can try out that one. I don't have a GPU on my machine. Unfortunately, I run this on the servers, so I will check it later. So hopefully this part of the code is also okay. So we have a loss function and the CPU part. So I'll drop it in the Jamboard slide number 12. Actually, we also don't have that much time already left. So I will briefly look in the slide number 13 with the one part missing here. So the next task, 11.3, I think, is to make the denoising autoencoder. So there is one small update to make it a little bit smarter. So that would be denoising autoencoder. Just a second, I will share. Okay, this one I shared. Denoising autoencoder. So this is a DEA, and it looks, so probably the easiest way is just to look at it, how it looks like. So the idea is that we will have a little bit different the incoming X and outgoing, so the incoming X and the ground truth will not be the same in this case. So we can apply some kind of random dropout to the input. By the way, you can do this in multiple ways. One is that you could probably try to apply dropout before the passing data inside the main loop, or change your data set to have this property. So there are at least two ways. So one is apply dropout. So there is already nice function. You can make your own dropout, or you can use the dropout inside the torch. So let me find what was the dropout inside the torch. I think it was just torch dropout. Yeah, torch dropout. So the dropout function is function without the parameters, and you can have it like it was a torch functional, I guess. Torch functional, torch, and then functional dropout. I will give you a reference. Or you can make your own random function, you know, like just a drop out, like replace with some probability the input pixels to zeros. That's it basically. So apply dropout torch and then functional dropout with some kind of p-value, so the probability, in this case 0.5 or whatever. So this function you can apply for the input, and then the output is clean image. So you can do this in two ways. So one is two options. One is in the data set get item. Another is in the main training loop. I would not advise to add this to the model itself, because at the end, when you train it, maybe you want to try it also with the clean images. Maybe you want to have only, let's say, half of images as a dropout and half as not as dropout. So for the dataset and training loop, that would be nicer to configure. So that is one. And the way how it looks like later is something like this. Here the zeros are white and the ones are black. But of course you can flip it around, you know, like just for visualization. With the grays, I think you can get this effect. So the noisy image, the model output, and then the real image. And if you train it in this manner, you automatically, just by applying this noisy input, get much stronger the decoder, and also, depending on the training protocol, the Z vector. So there is a literature regards to the denoising autoencoders. Quite interesting that just a small change have a lot of improvement. So I believe that you could do this yourself. The way, like, even if you don't understand about like how to use dropout function, you can just have the input matrix and go over for loop, and then have the random dropping of the pixels, so replacing with zeros. Or you can do like in some other way, like you're free to experiment and make it as you wish. So I think that's it for today. I will also prepare the task with a preloaded with a pre-trained weights. So you can, if you implement the model correctly, you can use the pre-trained weights. Basically, if you implement the model correctly, as I did today, I hope that all of the layers match the schema. If some layer do not match the schema, then the pre-trained model would probably not work. And even if you make your own model, I would accept that homework as well. The idea is that I would like then for you to calculate as for the distances. So I will formulate the task later as well for the homework. But in general, what I want to do is to work with the Z vectors. So just with the encoder part. So let me draw some very dumb, simple way. So there will be the encoder that is already pre-trained. So you don't need to do the training, right? And then you have, let's pass through the three samples. So one sample will be the A letter, the other sample will be the B letter, The third sample will be again the A letter, for example, or maybe let's make it more interesting. The last sample will be 8. So in this case, we would get 3 z vectors. So this will be the z1, and we don't care about the decoder part for this task. There will be z2 and z3. And then if we calculate with these embeddings the distances, so let me find quickly, or I don't want to write it myself right now. Cosine similarity, cosine distance, so that's just 1 minus the cosine similarity. So there is a dot product there. Let me find quickly the equation. Should I write it quickly, or can I just get it somewhere? So anyways, so the cosine similarity, I will later update the formula here, but you could use also cosine similarity or cosine distance. It doesn't matter actually, it's just the range, how it, like from -1 to 1 or 1 to or 0 to 2. So if you pass inside this formula, so let's say the z vector as an A and z2 vector as a B, maybe like that, you will get the output as one like similarity metric. And if you pass like for example these two inside this formula, you will get another similarity metric. And the interesting thing will be that these two will be much more similar than those other two. So what I want is for you to calculate the accuracy based on similarity. So finding the closest class that you can and calculate the belonging to the class, and then like the closest one would be the classified class, and then calculate the accuracy. So these two are more similar and these are like different with regards to that metric. So I will update this slide just in a second after our session, and I will formulate the home task as well. And I will provide you pre-trained weights for the encoder part. Probably I will also give you a code template, so you don't need to write that part. So just then you, but it will not include all of the code that was in this session anyways. Maybe I will just make like completely new model for you and pre-train it, and so that you cannot copy that one from your live session. That will be fun. So anyways, that's it for today. Hope this is interesting, exciting, challenging, and like if you actually for your like master's or bachelor thesis do something with regards to like developing all sorts of algorithms and functions and models. The models is the simplest part, but if you actually calculate, like make some kind of your own loss functions or your own normalization functions, or maybe some training procedures or algorithms, all of this counts as a real computer science. So that is much more interesting than just working on some applications. You can use this one for everything basically. So I hope that was fun. We'll meet tomorrow with more advanced models. Please do not put at the last moment the homeworks, otherwise it will be really challenging to finish this course. Okay, bye bye.